All right, hi everyone. Today we are going to continue our new unit on set theory. So we're going to start by just doing a direct comparison between our symbolic logic that we started with the beginning of this quarter and set theory, just so that we are all on the same page about the notation and what exactly each symbol means. So the first part here, we're going to just compare logic to set theory. So the first thing is the notation that we use. So in logic, we use P and Q, S, R, or all of those letters, and those are propositions. So these are lowercase letters that we used for our propositions. But in set theory, we use capital letters such as A and B, and these are sets. So proposition can be a sentence, whereas A and B sets, these are sort of groups of elements, essentially. To do a direct comparison between notation, if we had our not P notation, we would use the complement in set theory, so A prime essentially. And again, just to recap from yesterday, this is all of X such that X is not in A. Our third comparison is between and intersection, so P and Q. So we have A intersect B is equal to the set X such that X is in A and X is in B. So this is intersection. Our fourth comparison is between or and union. So A union B is equal to the set X such that X is in A or X is in B. So this is union. Our next one is if and only if. So P, if and only if Q. And this would be a quality between sets. So A equals B. So this is X is in A, which is equal to X in B. So essentially saying all of the elements in A are all of the elements in B. There's nothing that's in A that's not in B, and there's nothing in B that's not in A. So this is the idea of set equality. And then our last notation we had for logic was our if and only if. Or excuse me, our if then, not if and only if. We just did that one. So our if then statement, our implication statement, and so here, if for set theory, this would be a subset. So A is a subset of B, and we use this this notation here. It looks like a little C with a line underneath it, and so that is essentially saying if X is in A, then X is in B. So A being a subset of B is really saying that every single element that's in A is in B. But it's not a guarantee that everything that's in B is going to be in A. There might be other things that are in B that's not in A. But the rule here is everything that's in A has to be in B in order for A to be a subset of B. So let's do just a quick example of what that might look like. So let's start with, we have the set A is equal to the elements 0 and 1, and the set B is equal to the elements 0, 1, and -1. So we could say that A is a subset of B is true. And that's because everything that's in A, so 0 and 1, are in B. So everything that's in A is also in B. So A is a subset of B. However, the statement B is a subset of A is false, since -1 is in B, but -1 is not in A. So that doesn't meet our definition of subset. So we can elevate this idea of subsets with our familiar sets. So we talked about the integers, the rationals, and the set of reals, and then the various constrictions on those sets. So the non-negative, the non-zero, and the positive subsets of those larger sets. So we notate those 12 sets as the 12 familiar sets that we talked about last week. So let's look at an example here with some of those sets. So our first example, we have let A be equal to the set of rationals that are non-negative. And then the set B, let's be the positive reals. So we need to figure out if at all, these statements are true, or if any of them are false. So looking at this, I need to think about what is in each of these sets. And a good place to start is with 0, because that is one of the most restrictive values. We know that this, out of the 4 essential domains, the whole set, the set of positives, rational, we're looking at rationals. So let's just use the integers. Sorry, I always do a star, but it's more of an asterisk. So looking at this here, we know that 0 only is in the first 2 sets that I've written on the right-hand side. So 0 is a value that is most restrictive. And then we also have to think about positive versus negative, since that is also a sort of restriction here, because these 2 sets, are the middle 2 here, are the only ones that have no negative values in their sets. So that's something to think of as well. So when you're trying to decide if subsets exist between the 12 familiar sets, first think about 0 if it exists in both sets, and then whether positive and negative numbers both exist in both sets. So looking at set A, since we're going to start with, is A a subset of B? So again, we have to have every single value that's in A be in B. So looking at A here, I note that it does include 0. It is the non-negative rationals. However, the R, the set of reals for B, are strictly positive, so that does not include 0. So that is kind of my ticket out here. It is false, so we can say is false, since, let me move this down, is false since 0 is an element of A and 0 is not an element of B. So that's kind of your ticket out there. But let's look at B being a subset of A. So looking at our 12 familiar sets, from least restrictive to most restrictive, in the sense of, well, let's do it the other way around. Let's look at most restrictive to least restrictive. So we looked at that kind of diagram last week with sort of I would consider those Venn diagrams, the Russian nesting dolls, if you will, that we created. So looking at this, we have the set of integers, I would say, is the most restrictive, then the set of rationals, and then the set of reals being the least restrictive. Meaning that there are definitely more values in R, and there are less values in Z. But all of the values that are in Z are in R, and all the values that are in Q, well, all the values that are in Z are in Q, and all the values that are in Q are in R. So we can say that Z is a subset of Q, which is a subset of R. So that is kind of the strain of this. So when you are saying that a least restrictive subset, or you're questioning if the least restrictive set is a subset of a more restrictive set, the answer most of the time is going to be no, that is not the case. And these ones are easy to figure out because obviously there are a lot of things that are in the set of reals that aren't in the set of rationals. Take for instance pi. So pi is in B, but pi is not in A. So we can use that as our example here. So B is a subset of A. Well, this statement is false. Since pi is in B, but pi is not in A. So in this case here, A and B are not subsets of each other. Both of those statements were false. So let's do another example here. So let's have A be the set of all reals, and B is the set of positive integers. So we want to consider A being a subset of B, and B being a subset of A. So again, let's look at, let's start with 0. So let's see, is 0 in R? Well, let's pause, because this sentence, or this statement here, is saying that we have a least restrictive set, R, being a subset of a more restrictive set, and that's not going to be the case. So we can just find a counterexample. We can use pi again, that's fine with me. So this statement is false since pi is in A, but pi is not in B. So now let's look at the B being a subset of A. So let's take a look at 0 here. So 0 is definitely in A, that is the set of all real numbers. 0 is not in B, but we're trying to say, is B a subset of A? Well, if 0 is not in B, then it doesn't really matter if it's in A or not, so that's not going to help us out there. So let's look at all of the positive values. So the set of integers, the positive integers, that is going to be everything from 1 to positive infinity. So I have to think about, are all of those values going to be in the set of all reals? Well, yes, they will be, because the set of all reals is the least restrictive set. So in this case, B is a subset of A. This is a true statement, since all of Z is or all of Z plus is in the set of reals. So from here, we're going to pause because you have a practice set to do for tomorrow, and there are I think 10 questions on there. So I want to give you time today to start that so that you can formulate questions that you may have for me, so that tomorrow on the Zoom call you can ask any questions that you may have. So you have no classwork officially due today. You just need to fill out the Google form indicating that you've watched this video, and then tomorrow you have a classwork assignment. It's about 10 questions. I apologize, actually. There is one other thing that I wanted to go over that I missed on Monday. So, and that is on your classwork. So hopefully, if you pause this video and you were going to exit out, please tell your friends to come back if they are confused on the first couple questions. So this has to do with the set of rationals. And this is showing that a number is a rational number if it belongs in Q. So let's take the number, so let's let x equal 0.37 repeating. So our definition of a rational number, so the set Q, is x such that, or excuse me, not x, a over b such that both a is in Z and B is in Z. Obviously, it gets a little bit more restrictive as you go on, but we just want to look at just all of the rationals. So it makes sense that 0.37 repeating would be a rational number, because we know that regularly our definition of rationals is that we have either a pattern or the decimal ends, and that's essentially a rational number. So here there is a pattern going on where 37 is repeating. However, it's not a typical fraction that we may know, like 0.66 repeating, where we know that that's 2/3. So we want to be able to show that these decimals are, in fact, meet the definition of a rational number, where we can put it into the form of a over b. And there's a really easy way to do this. So we're going to actually use a system of equations to show that this is a rational number. So I'm going to start with, I'm going to multiply both sides by 100. So we have 100x is equal to 37.37 repeating. Then I'm going to take the original x value and I'm going to subtract this. So now, the cool thing that happens is that this repeated decimal is going to cancel out from the original value. So I'm just left with 99x is equal to 37. And now I can say x is equal to 37 over 99. So now, this is equal to 0.37 repeating, and I've just shown that this repeating decimal does in fact meet our definition of a rational number, because 37 is an element of Z, and 99 is an element of Z. So this meets our definition. All right, so now that's the last piece of new information that I have for today. Again, please submit the Google form, and then you can go ahead and get started on the classwork that'll be due on Tuesday, but I have posted it in case you want to get started on it now. And again, there is no Zoom call today. There will be one, however, tomorrow, in case you have any questions on this lecture. All right, have a great rest of your day, everyone.